The cannonball in this animation leaves the cannon and curves downward in a familiar way. Why do all objects projected horizontally have a similar shape? To understand how an object moves when it's thrown horizontally, we must first look at its velocity in the horizontal direction. When an object is thrown horizontally, its entire motion before it leaves the thrower's hand is in the horizontal direction. Once it leaves the thrower's hand, it now has two velocities, horizontal and vertical. This just means that it moves with a certain velocity in the horizontal direction and with another velocity in the vertical direction. It might be unusual for you at first to see that a single object can have two velocities, but this view is essential to understanding this type of motion. Let's look at the three spheres in this animation. While the spheres are rolling along a flat surface, since the net force on them is zero, they have only one single constant velocity in the horizontal direction. The moment the red and blue spheres leave the table, they have two velocities, the horizontal velocity they had on the table and the floor, and the vertical velocity that comes from the vertical force of gravity. Now that we've established that an object thrown horizontally has two velocities, horizontal and vertical, let's look at the physics of just one of those velocities, the horizontal. In the absence of air friction, the horizontal velocity of a sphere thrown horizontally is constant after it leaves the thrower's hand and before it hits the ground. Why is this? This is because the force of gravity is a vertical force, so that it only changes vertical motion. Newton's second law tells us that if the net force in the horizontal direction is zero, then we should expect the horizontal velocity not to change. What does it mean that the horizontal velocity is constant? Focus on the horizontal position of the ball as it moves from left to right. Notice how the ball changes its horizontal position by the same amount each equal interval of time. Now let's focus on the vertical position of a marble projected horizontally after it leaves the mechanism. Since the marble in this video is projected horizontally, its initial vertical velocity is zero. When it leaves the mechanism, the constant vertical force of gravity increases the vertical velocity of the sphere by 9.8 meters per second every second. Since the marble on the left and the marble projected horizontally begin with a vertical velocity of zero, they have the same vertical drop and velocity at every moment before they hit the ground. As you can see in the video, the marbles hit the ground at the same time. Let's look at this again. Notice that each sphere has the same vertical position at all times. Each sphere also has the same vertical velocity and vertical acceleration. The most important thing to notice is that since each ball is launched from the same height, they hit the ground at the same time. Now let's look at what would happen if three spheres were projected horizontally from the same height that an object was dropped. Each sphere in this situation has an initial vertical velocity of zero. For all four spheres, the vertical force of gravity will add 9.8 meters per second each second that the spheres are in the air. All four spheres will have the same vertical velocity for the entire time they are in the air, and they will hit the ground at the same time. All the spheres in this picture have a single downward force that is changing only their vertical velocity. That force is the vertical force of gravity. The sphere that lands on the far right, of course, was given the greatest horizontal velocity by the thrower. Since the friction in each sphere is negligible, the horizontal velocity of the three spheres that were projected horizontally will not change the entire time they are in the air. So now you've learned that when an object is projected horizontally, it has two velocities, horizontal and vertical. When the ball leaves the thrower's hand, its initial vertical velocity is 0, and the vertical force of gravity increases the vertical velocity by 9.8 meters per second for each second that it's in the air. We call the ball's horizontal velocity Vx and the vertical velocity Vy. Vx is determined by whoever or whatever throws the ball. And since the only force on the object is the vertical force of gravity, the Vx is constant. The initial vertical velocity of the ball when it leaves the thrower's hand is 0. Once again, remember that only the vertical velocity is changed by the force of gravity. Let's look at a specific example. A ball is thrown horizontally with a velocity of 4 meters per second. Let's look at the vertical and horizontal velocities of the ball after it leaves the thrower's hand. Since the vertical force of gravity only changes the vertical velocity of the sphere, we know that the horizontal velocity of the sphere will not change. Since it was thrown with a velocity of 4 meters per second, it will maintain a horizontal velocity of 4 meters per second the entire time it's in the air. To make the math a little easier, I'm going to round off the acceleration due to gravity, which is actually 9.8. I'll make it 10 meters per second squared and show what happens to the vertical velocity of the sphere. So for the 4 seconds the sphere was in the air, the horizontal velocity remained at its initial value of 4 meters per second, and gravity increases the vertical velocity by about 10 meters per second each second. Let's review a few conceptual points before we end this lesson. The pink sphere on the left is dropped at the same time and the same height 3 other spheres are projected horizontally. It's probably not obvious at first, but these 4 spheres have a lot in common. First, they all have an initial vertical velocity of 0. The only force on both spheres is the vertical force of gravity. For every second they are in the air, they have the same vertical position, vertical velocity, and vertical acceleration, that is negative 9.8 meters per second squared. And the most important thing to remember is that all the spheres hit the ground at the same time. Let's try to solve a problem with an object propelled horizontally. A rock is thrown horizontally from the top of a cliff at 150 meters per second. How long does it take the rock to fall 45 meters vertically? Since the rock is thrown horizontally, its initial vertical velocity is 0, and the vertical force of gravity will give the rock a vertical acceleration of 9.8 meters per second squared. Since we are trying to find the time it takes for the rock to fall 45 meters vertically, we write t equals question mark and dy equals 45 meters. Since the rock was thrown horizontally with a velocity of 150 meters per second, we put that info on the horizontal side of the table. Since time is neither x nor y, I can put time on the x side too. To solve this problem, we need to find an equation that either matches all the variables on the vertical side or all the vertical variables on the horizontal side. Well, it's pretty easy to see that we have many more variables on the right side, so the equation that fits is dy equals vit plus 1/2 at squared. When we do the math, we get an answer of 3.0 seconds. Since the vertical force of gravity only changes a projectile's vertical velocity, the horizontal velocity is constant. Therefore, there is only one equation that allows us to find the horizontal position of a projectile. That is dx equals vx times t. And this is the end of my first presentation on a projectile fired horizontally.